Ever wondered how programmers fix errors in their code? Well, they use a process called debugging. This isn't about squashing tiny insects, but rather, it's about sorting out those pesky little errors or bugs that crop up in computer programs. These bugs can stop a program from behaving as expected, and that's where debugging swoops in to save the day. Debugging isn't some haphazard guessing game. It's a systematic approach to problem solving. It's like being a detective, meticulously hunting down clues, identifying the culprits causing the issues, and then fixing them. This process is an essential skill in the programmer's toolkit, and without it, we'd be stuck with a lot of faulty software. So how do programmers debug their code? Well, there's a whole host of techniques and tools at their disposal. Let's dive into some common debugging techniques and tools used by programmers. First up, we have print statements. These are a basic yet effective way to debug your code. When you're dealing with a bug, it's essential to understand what's going on under the hood of your program. Print statements help us do just that. Imagine your code as a mysterious black box. You can't peer inside to see what's happening, but print statements can serve as little windows into this box. By strategically placing these statements in your code, you can track the flow of your program, one step at a time. But how do you insert them? It's simple, really. Wherever you want to check the value of a variable or trace the program's execution, add a print statement. It will display the information you need, right there in your console. And there you have it. While simple, print statements can be a powerful tool in a programmer's debugging arsenal. Output. Next on the list is using a debugger. Now, what exactly is a debugger? In the simplest terms, it's a tool that programmers use to inspect their code, identify errors, and understand how their program is behaving. Imagine you're a detective trying to solve a mystery. A debugger is like your magnifying glass, spotlighting clues and helping you connect the dots. It's an all-seeing eye that can peer into the very heart of your code, revealing what's happening behind the scenes. Let's take a closer look at how to use a debugger. For this discussion, we'll use GDB or the GNU debugger as our example. Once you're in GDB, you can set breakpoints, which are like stop signs that halt your program at specific lines of code. This allows you to examine the state of your program at these critical junctures, much like a detective might examine a crime scene. But the fun doesn't stop there. With GDB, you can also step through your code, line by line, watching how your program behaves with each execution. This is like following footprints in a detective story, tracing the path your program takes as it runs. And what about those mysterious variables, changing their values as your program runs, like characters in a mystery novel changing their alibis? No worries, GDB has you covered. With the print command, you can inspect the values of these variables at any point in your program, revealing their secrets and helping you understand their role in the grand scheme of your code. But perhaps the most powerful feature of a debugger is its ability to analyze the execution flow of your program. With this, you can see how your code is structured, how different parts interact with each other, and where potential problems might be lurking. In conclusion, a debugger is more than just a tool. It's a companion that guides you through the complex maze of your code, illuminating the path and helping you find and fix errors. A debugger is a versatile tool that provides detailed insights into the program's execution. There's a wide range of other debugging techniques at your disposal. Next on our list is logging. This technique involves writing messages to a log file or the console. These messages provide valuable insights into the program's behavior and can be instrumental in tracing errors back to their source. Remember, a well-placed log statement can often tell you exactly what's going wrong and where. Next up, assertions. Assertions are conditions that you expect to be true at a certain point in your program. If an assertion fails, it triggers an error message and halts program execution. This is a powerful tool for catching unexpected behavior before it spirals into a more significant problem. Moving on to static code analyzers. Tools like Clang Static Analyzer or CPP Check perform a static analysis of your code, identifying potential issues without even running the program. They examine your code for common errors and bad practices, helping you catch bugs early in the development process. Now let's talk about memory debugging. Memory-related issues can be particularly tricky to debug. Tools like Valgrind can be incredibly helpful for this. They detect memory leaks, undefined memory access, and other memory-related errors, helping you maintain the health and efficiency of your program. And lastly, don't forget the features provided by your Integrated Development Environment, or IDE. Features like code highlighting, syntax checking, and built-in debugging tools can save you a lot of time and headache. They can spot errors as you type, highlight potential issues, and even suggest fixes. Remember, debugging is not just about fixing errors, it's about understanding your program. Each of these techniques offers a different perspective on your code, a unique lens through which you can understand what's happening under the hood. And here's an important point to keep in mind. There's no one-size-fits-all solution to debugging. Different problems call for different techniques. The key is to familiarize yourself with a wide range of tools and techniques so you can choose the most effective approach for each situation. Each of these techniques has its strengths and can be remarkably effective when used correctly. Prevention is better than cure, and this holds true in debugging as well. In the realm of programming, taking preventive measures can save a great deal of time and effort. Two of the most effective preventive strategies include code review and unit testing. Let's start with code review. It's essentially a process where another person carefully examines your code to spot any errors or inconsistencies. This is a classic case of two heads being better than one. The reviewer brings a fresh perspective, potentially catching bugs that might have been overlooked by the original coder. In addition to detecting bugs, code reviews can also improve the overall quality of the code by enforcing coding standards and promoting best practices. They can even serve as a learning opportunity, allowing developers to share knowledge and learn from each other's experiences. Next, we have unit testing. This involves writing small tests for individual components or functions of the code. Each test checks whether a specific part of the code behaves as expected under given conditions. The beauty of unit testing lies in its ability to identify issues at the earliest possible stage, often even before the code is integrated into the larger system. Regular unit testing can help maintain code quality by ensuring that changes or additions to the code do not break existing functionality. However, it's important to remember that neither code reviews nor unit tests are a silver bullet. They are just part of a broader toolbox of techniques and strategies for preventing and fixing bugs. In conclusion, debugging is not merely about fixing bugs, it's about understanding why they occurred in the first place and taking steps to prevent them from happening again. When it comes to debugging, an ounce of prevention can indeed be worth a pound of cure. Regular testing and code reviews are essential practices that can help maintain code quality and prevent bugs from reaching the debugging stage in the first place. Remember, effective debugging is a systematic process, and these tools and techniques are there to assist you in this task. Before we wrap up, let's quickly recap what we've learned about debugging. Debugging, as we've discovered, is a pivotal skill for all programmers. It's all about systematically identifying and resolving issues in your code that prevent it from operating as intended. We started with the simplest but sometimes the most effective technique, the use of print statements. By displaying variables and tracing the program's flow, we can pinpoint the location of errors. Then we delved into the power of a debugger, which allows us to step through the code, inspect variable values, and set breakpoints. We also explored the concept of logging, which involves writing messages to a log file or console. These log messages can provide valuable insights into your program's behavior, helping you spot anomalies. Then we discussed assertions, which are crucial for checking whether certain conditions are met. If an assertion fails, it usually triggers an error message and stops the program. Next, we introduced static code analyzers like Clang Static Analyzer or CPP Check. These tools perform static analysis of your code and identify potential issues. We also discussed memory debugging tools like Valgrind, which detect memory leaks, undefined memory access, and other memory-related errors. We then discussed the advantages of integrated development environments, or IDEs, which provide features such as code highlighting, syntax checking, and built-in debugging tools. We emphasized the value of code review, giving another set of eyes the chance to spot potential issues and offer insights. Lastly, we talked about the importance of unit testing in validating the correctness of individual functions or modules. But remember, the key to effective debugging is a systematic approach. Identify the symptoms, narrow down its location, and then fix the issue. Regular testing and code review practices can also help prevent bugs from even reaching the debugging stage. With these debugging techniques and tools in your toolkit, you're well equipped to tackle any bugs that come your way. Happy debugging!